In these examples, we're given a function and asked to determine inverse function values. And for these, I want to show how we can find these inverse function values without actually determining the inverse function. To understand how this works, we need to remember that the inverse function undoes the operation of the original function f of x. So if x is the input into the original function and y is the output, this y value becomes the input into the inverse function, which returns the original value of x. Which means we can find these inverse function values if we can find an input into the function f that has an output of 4 and 6. So to get started, let's use an input that's a perfect square. Let's determine f of 4. Well, f of 4 would be equal to the square root of 4 plus 1. The square root of 4 is 2. 2 plus 1 is equal to 3. We want an output that's equal to 4 or 6. So this isn't going to work, but notice how 3 is close to 4. So let's try another input. 4 is 2 squared. Let's try the next perfect square. 2 squared was 4, and 3 squared is 9. So let's determine f of 9. f of 9 would be equal to the square root of 9 plus 1. Well, the square root of 9 is 3 plus 1, which is equal to 4. So notice how when the input is 9 into function f, the output is positive 4. So if this output becomes the input into the inverse function, then the output of the inverse function is going to be positive 9. So this tells us that f inverse of 4 is equal to 9. Again, f maps 9 to 4, and the inverse function maps 4 back to 9. Therefore, these two functions are undoing each other. Now let's see if we can find an output for function f that's equal to 6. Well, 3 squared is 9. Let's try 4 squared, or 16. So f of 16 would be the square root of 16 plus 1. Well, the square root of 16 is 4, plus 1 is 5. So that's not going to work. So let's go ahead and try the next perfect square, which would be f of 25. That's going to be the square root of 25 plus 1. The square root of 25 is 5. 5 plus 1 is equal to 6. Notice how the 6 is the output of function f, which matches the input for f inverse of 6. Also notice the original input for function f was 25. So when function f has an input of 25, the output is 6, which means when the inverse function has an input of 6, the output is 25. So as long as the given function f of x is not too complicated, we can often use this method for determining inverse function values rather than finding the inverse function and then evaluating the inverse function at 4 and 6. Let's try a second example. Here we're given g of x equals 2x minus 1. We want to determine g inverse of 3 and g inverse of 7. Which again, our goal is to find an input into function g so that the output will be positive 3 and positive 7. So looking at function g, notice g of 2 would be 2 times 2 minus 1, which is equal to 3. This is exactly what we wanted. So if g of 2 equals 3, then g inverse of 3 is equal to 2. To evaluate g inverse of 7, we want to find an input into g so that the output is equal to positive 7. So notice if we had 2 times 4 minus 1, that would be 7. So g of 4 would equal 2 times 4 minus 1, or 7. So in g, when the input is 2, the output is 7. Therefore, g inverse of 7 is equal to the original input of 4. I think understanding how this works is helpful to really understand the relationship between a function and its inverse. I hope this was helpful.